Okay, thanks, Carlos, and thanks for allowing me to speak here. It's a fantastic workshop so far. And what I want to talk about is, again, as Maxime said, when you combine stability and Fukaya categories, some great things happen. There's some miraculous harmony. And I want to just give one very specific example. Kind of tame, so the most formed parameter families of stable objects. But you can see it will be already, these spectral networks will already be sort of arbitrarily, have arbitrarily many vertices and so on. And will have the benefit that you can explicitly see everything that's going on. Actually have sort of a complete list. So remember the general proposal, the special case of Maxime's program. So in general, you have some Fukaya category with coefficients. There should be some base, symplectic manifold, some holomorphic volume form. And the fiber, it's not really something in symplectic geometry, but you can just view it as some category with stability condition.
You don't need volume element on the base in this case. Stability will be very some canonical point.
Yeah, so either, I'm doing a simplified version
Yeah.
where you don't, the central charge is fixed, not.
But
I can product.
no, but if you want to speak about special Lagrangians in the base, do you need the volume? Say what
No,
it-
but it will be associated to volume
So
stability.
you could think of this as being kind of part of the central charge. More generally, this would be part of the central charge on the stability condition. I want to simplify things pretty radically. So, well, in my case, will just be a single category, so trivial constant coefficients. And also the stability condition in principle could vary depending on the point in the base on this category. But my talk will be just a constant stability condition. So some stability condition. And in fact, I'll look at a very specific category with stability condition and base, but we'll sort of zoom in and make it more and more special. So what did, so the goal is here to claim that there construct a stability condition on sort of the total category of this local system of categories. So if my local system is just a trivial constant local system, this will be just the product of the entire category of the base, tensor product, with the fiber category. So this is here. Both these are constant in P. And more precisely, the stable objects for this stability condition which you want to construct should be these singular Lagrangian graphs, or in higher dimension, singular Lagrangian skeletal or submanifolds in the base. Okay. And so, yeah, the simplest categories that I can think of triangulated are sort of type AN. So in my case, this fiber category with the category associated with the AN quiver. Which I'm just going to call curly n. fiber a little bit in quotes. It's not geometric, but it's non-commutative. It's a category with stability condition. And I also want to make things kind of as nice as possible. I also want to look at a very specific stability condition on this, the kind of most symmetric one.
And do you have any orientation? Yeah, so it doesn't depend on the orientation.
Yeah, this category doesn't depend on the orientation of the arrows. Where kind of comes from the regular n+1 gon. So I have every indecomposable object is stable. There are just finitely many of the shifts. And central charges are, so these correspond to diagonals in this n+1 gon. And the central charge will be just the difference of the two vertices, so some difference of roots of unity or up to some overall factor. See central charge of any stable object. Difference. N plus first two roots of unity. Or some positive real number.
So in principle, I could implement that by taking a category of disk with n+1 stops and.
Yeah, that's a good point. Oh, so
And with potential exponent, zip-to influence.
yeah, just
No,
monomial
but
instead
I-
of polynomial.
What I wanted to ask is, should I view this project as thinking about that fiber as big or small?
Small.
Fibers are small.
Yeah.
Yeah, so in the project, kind of, cannot take a product of arbitrary stability condition. Kind of one of them is just some arbitrary category with stability condition, but the other thing really needs to be something geometric, which comes from some holomorphic volume form. But in my case, both will be actually the same, but just one has the interpretation as a category with stability, and the other sort of remember that it's an actual geometry. So. Yeah, and of course this has many other stability conditions. I'm just taking the one which is the most symmetric to make.
So to what is this?
Are diagonals oriented?
Or objects.
Well, to each diagonal actually corresponds. You have all the shifts, so each diagonal corresponds to an integer family.
Take the difference at vertices, right? Did I understand correct?
Yes, yes.
Yeah, any difference either way.
So you need to order.
Yes, so we shift by one.
Yeah, so there's many objects, and central charges of these objects are either something this or the other difference, one of these two, depending on the shift.
The heart of the structure go up, some direction.
Yeah, objects in RWT structure, I orient everything upwards, as in.
But heart of the structure depends on the orientation, right? So
Yeah, if you rotate this thing, you get different.
Structures.
Yeah. I don't really care about the T structure so much, just about the actual list of stable objects, which will not change if you rotate the picture.
and so the central charge of vertex is
No,
the
only
difference-
for edges. Central charges for edges.
Objects correspond to, it's like Fukaya category.
No. For but
It's upper n will.
like Maxim's talk, there was a number attached to every vertex.
You can see the.
And that's the difference
n
of-
sides of n+1 gon.
So it's a difference of two consecutive roots of unity of degree n+1. Right?
Yes, yes.
Okay. Yeah, so as I said, the base sort of has to be something, it cannot be just a category with stability, it has to be something actually geometric. And all this has a simple geometric interpretation. So my base here will be this Landauer-Ginzburg model. C with potential Z to the, could be different, n plus 1 integers. And tiny chalk. So what it means is my holomorphic symplectic form, holomorphic volume form should be something exponential e to the power of this van der Waals potential. Maybe some overall factor also. And the category and stability condition associated with that is exactly of the type here. Sidle this AM category. And how do you? Maybe I'll first explain. So the category which you want to construct a stability condition on will be a product AN tensor AN. And so it looks like we've taken the simplest possible assumptions of a fiber and base, but turns out this case is already sort of almost as hard as the general case in some ways for general N and M. So I'll look at specific N and M also, and only then does it become easy enough that you can actually explicitly write down the whole picture.
So it's just a different realization of the same case.
Yeah, it's kind of one thing. Here, just think of it, the fiber is just some category of stability, and here I think that there's some geometry in the background, which is this disk with this holomorphic volume form.
But this category itself is a Fukaya side of category.
Yes. That was.
What?
This tensor product itself is a Fukaya side.
Yes, it's, you can think of it, but if you want, you can think of it as Fukaya sidle of x to the n plus 1 plus 5 n plus 1. Or it's for this quiver, which if you take the tensor product of path algebras, you maybe orient everything the same way. Here, n columns, and rows. And I have relations in this quiver that squares commute. Okay. The first thing to look at for this category is it's just some quiver, but to understand it, the first thing you want to look at, it actually has dimension. So it's fractional Calabi-Yau. Some useful observation here. Take, in general, it's not so clear what the dimension of a triangulated category is, but in some cases, it's like a good candidate. See, is fractional Calabi-Yau. So Calabi-Yau usually would mean that the Serre functor is some power of the shift functor, and fractional that some power holds stably. So nth power of the Serre functor, C has. I need to assume it has a Serre functor. And then fractional Calabi-Yau means that the nth power of the Serre functor is shifted by some shift. Well, then it's, by definition, the dimension will be n per n.
But N and M are symmetrical.
Different.
PQ.
But this C is a fiber category.
I want to apply it to this category. But here, it's just a definition of what fractional Calabi-Yau is. So for some certain categories, it's kind of clear what their dimension should be, even though it's not clear to know. It's going to be pure E. Yeah, so many of you know this. Yeah, it really turns out that there's an invariant here. It's very easy to compute and also tells you a lot about the category. So, lucky thing. So, so AN itself is fractional Calabi-Yau. Example. It's AN category. Because it's the higher category of a disk with n+1 marked points. If I rotate, CR functor is kind of rotation by 1 over n+1 for a full rotation. So we have some relation. CR functor goes to shift by -1. It's rotation 1 click counterclockwise to the n+1st power and shift by 2. You rotate a full circle in the Fukaya category, you change the grading by 2. And therefore, the other dimension n n-1 over n+1, number between 0 and 1. And if I have a product, if I have a tensor product, I'll just add the dimensions. So the Calabi-Yau dimension an1. Okay, some okay, these numbers ni plus 1 rational number. Yeah, kind of gives you some first kind of what to expect about this category. It actually turns out if we make a table, the Calabi-Yau dimension of some product, if it's less than 1, strictly less than 1, then ni minus 1 over n minus 1
dimensions.
over n plus 1.
Minus 2.
You put the minus 1 on the other side.
Yeah.
Alright. Yeah. At the very end.
So is it -2 by any chance rather than 2?
Ah. Minus 2.
Otherwise it doesn't work.
Yeah.
Okay. Yeah, thanks.
-1 and
Minus 1 and minus.
Okay, sorry. Yeah. You're very correct. The sign is wrong. So, yeah, so definitely this should be true. And so what does this Calabi-Yau dimension tell you? In the cases where it's strictly less than 1, representation type turns out to be finite. So I'm taking some product and I'm looking at compute this dimension. So finite means there will be finitely many indecomposable objects up to shift. And there's very limited cases where this happens. So just A2 tensor happens for AN. Then you have a non-trivial product for A2 tensor A2, A2 tensor A3, A2 tensor A4. If you look at the corresponding singularities, this is like x cubed plus y cubed, Landau Ginsburg model. Turns out to be Morita equivalent to the bounded derived category for quiver. This is E6 singularity. This is E8. So, I mean, there's some non-obvious statement here to check that if you take these actual quivers, you get two different algebras and that they're Morita equivalent, but if you just look at the corresponding singularities, it's the same.
Is it a general statement that the fractional diagonal dimension of the general is
Not completely sure. Yeah. I mean, it's
Experimentally,
I mean, if it's finite representation type, we can sort of see that it has to be fractional Calabi-Yau probably, because it's not too many functors, and at some point it gets shifted. Yeah, but I'm not sure in general. I'm just claiming in these cases.
So if you take another Denkin quiver, what will be this fractional number? Is it like 1 minus 2 divided by Coxeter number, something like that?
Yeah, it's Coxeter number minus 2 over Coxeter number. So, I mean, yeah, in this case, here it has to, of course, be the same fractional number. Yeah, then the can also equal exactly 1. It's kind of like Calabi-Yau 1. Yeah, it doesn't mean that it has to be a Calabi-Yau 1 category, but it stably behaves like Calabi-Yau 1 category. So these turns out to be tame. And there's also, again, just 3 cases. Elliptic singularities, so E2, answer E2, answer E2. 1/3 plus 1/3 plus 1/3. We have A3, answer A3, and A2, answer A5. Yeah, and then the general case, Calabi-Yau dimension bigger than 1 will be Wald representation.
E2 is 3, 5. Last is 4 plus 3. E2 is 3.
Which?
The last case is E2 times A3 one factor. A3. E2 is 3, 5. Last case.
No.
1/3, 1/6. You're right, you're right. Sorry.
Yeah, it's kind of the E8 singularity is it's square, cube, 6 pound. Okay, so these are all oddities.
What are these singularities again? Which elliptic singularities do these 3 cases correspond to?
Just add 1 to this number and make the corresponding. So x cubed plus y cubed plus c cubed. Here, yeah, x to the 4th plus y to the 4th. Yeah, so
like E6, E7, and E8. I find.
yeah, maybe a fine.
6,
Yeah.
E7, and E8.
Maybe it has several names. So these were actually considered by Ueda. As sort of Fukaya style categories, and we'll see that these have some nice sort of B model interpretation. You can think of this, it's almost like elliptic curve, it will turn out.
It is elliptic curve modular some like Z,
Yeah, yeah.
Z3, Z4, or Z6, especially elliptic curves modular.
Yeah. Yeah, so I just want to say, why do I care about this in the context of the spectral network? Because you can, a priori, you know that in these finite cases, you only have finitely many different spectral networks corresponding to stable objects. In these tame cases, you only have one parameter family of spectral networks. And then in the wild case, you'll have arbitrarily complicated spectral networks. I mean, it could be, for a particular stability condition, it could be simpler, but generically, it's the worst that can happen. Yeah, so maybe let's look at the, maybe mention so these categories, how can analyze them, that they correspond to something.
Does it mean that in the wild case, you automatically have to have at least 2 parameters, or could there be a 1 or 0 parameter case also in the wild case?
Yeah, some objects might have less parameters, but there will be an object which,
In the wild case, there's always has to be objects.
for arbitrarily large integer, there will be some family of objects which
With at least one.
with that modulation. Okay, so these cases are parallel, so they turns out.
Actually, why is that? I mean, you might have imagined that all the wildness came from extensions between stable objects, not from the stable families themselves.
Yeah, so, I mean, there might be some. There's, of course, you can put a stability condition on AN tensor M, which only has finitely many stable objects.
Oh, okay.
But I'm saying, kind of, yeah, for all stability conditions, the worst that can happen. And we'll see that these stability conditions, which are products of these kind of stability conditions, we see the full category. The extensions are not hidden. Yeah, so another way to understand this, which will turn out useful for us, is that this is dB of the curve static quotient C mod 6 action. You take the elliptic curve, which is this moduli, the C mod 3. C mod 3 overfill point in the moduli. And so what is this quotient? It's going to be a P1 with 3 overfill points. C mod 2, C mod 3, and C mod 6. So the whole thing is, of course, rigid. If you had more overfill points, there would be some parameters. But since this guy is rigid, no parameters here. I mean, you could take a C mod 2 quotient of an elliptic curve, but it will not be realized as such an algebra. And this was, yeah, so this equivalence is contained. Many people know about it, but it's definitely contained in this paper by Ueda. On homological mirror symmetry for elliptic singularities. It's a sort of little bit indirect proof using Orlov's theorem. But I'll explain how you can discover this equivalence sort of by looking at spectral networks here. It's kind of like you build in mirror symmetry the SYZ mirror by looking at special Lagrange vibration. Here you can look at certain spectral networks, and their moduli will be this P1 with 3 orbital points. So that will be a way to see this equivalence. In a sense. Yeah, but yeah, that's right. I mean, what this stating is just that there's some exceptional collection in this category, which you get this A2 tensor back quiver. But
Я give some lectures. Такой нормальный lectures.
okay, yeah, so it's okay.
So
Known for a long time.
So if you have any singularity which is given by some powers, this corresponds to such situation. Yeah. So
Yeah.
like you say, you add 1 to the powers. So in particular, these finite and elliptic singularities are exactly those which have an equation which is the form x to something plus y to something plus z to something equals 0. Right?
Yeah.
Like E7 doesn't have that representation, so it doesn't appear here, for example.
Yeah, E7 cannot appear.
It has a mixed monomial, so that's why it doesn't.
Yeah. I think this is called ADE chain or something, representation theory. A2, D4, D6. And of course, there's the 2 other cases will be some other quotient of elliptic curve, or take the different elliptic curve, rectangular. That is.
So also in the wild case, this corresponds to singularity z squared plus x to the power first index plus 1 plus y to the power second index plus 1. Right? Something like that.
Yeah, I mean, I think we expect, I'm not sure if this is proven for
Or 1 not
Fukaya
square,
Seidel
but the
category.
first index plus, yeah.
Some punitive formula for Fukaya Seidel category that
Yeah, it's
Fukaya
pretty
Seidel
good.
category is a tensor product. I mean, it's definitely expected. I'm not sure.
And also if you have many factors, then you will get hypersurface and high dimensional space. Like if you have many factors,
Yeah, but yeah, we care about it more from the symplectic point of view. That so you can also deform the polynomials a little bit each individually. Okay, so that's the categories. It's something you can understand pretty well. And I want to get back to what are these spectral networks, which I want to find in these cases. Yeah, what I took this little bit, this holomorphic volume form to explain that.
Again, just
Yeah.
remember, spectral networks means the same described in
No. Yeah, it's
Okay,
more
so-
related to Monday's Maxim's talk than to today's Maxim's talk.
So it will be spectral network on this elliptic with 34 points, or where?
No, in my base. Here, it will be as in this Landau-Ginsburg model, so on the disk.
So
as you can
what
see.
is the spectral network? On
Yeah, I'll
the
explain.
ground?
But first, I want to explain this the holomorphic volume form which I chose. This, yeah. It defines a flat metric. You get the flat coordinate is just obtained by integrating this. E to the z m, sorry, m plus 1. It's the same as was before.
M.
And I just m.
Last time it was M, but
Yeah. It's an integer. Positive. So it gives you a flat metric, and what that flat surface looks like, you get just complex plane, but not the usual flat metric, but some other flat metric, which is rescaled by this factor. And for this, just if I take this monomial instead of this generic polynomial, what this looks like, I get some points at infinity. So, I mean, what am I drawing? I'm just drawing, there's a map from C, which is given by integration, a local isometry from this funny metric I put here to the standard flat metric on here. Will be local homeomorphism. And what I'm drawing over here is the picture downstairs. And this kind of covering, almost covering local homeomorphism, it's ramified at roots of unity up to some scale. And here. And it's ramified here sort of infinitely, so you can imagine an infinite spiral staircase going up and down. It's kind of infinitely many sheets, helix over each of these points. But this will all be irrelevant. What really matters is just everything will happen inside this regular m plus 1 bond. M plus 1. So the C upstairs gets mapped multiply to this plane and ramified over here, and this point actually is at infinity in the C upstairs.
You're including some spectral networks.
Not yet, no. The spectral networks will be here, and they will all sit inside this n plus 1 column. So they should end at these points at infinity. That means that picture upstairs, they should go to infinity in a certain direction, corresponding to roots of n plus first roots of infinity. Okay, so yeah, what is a spectral network? Morally, it's some special Lagrangian, which some degenerate limit became a graph in this regular pentagon, or n-gon, n plus 1 gon. So, yeah, there should be some first of all graph with straight edges. It's flat metric. And endpoint should be these points at infinity over here where this covering is infinitely magnified. Endpoints at n plus first infinity. So, yeah, I mean, you can, it's not really important that it's a regular. I'm just making everything regular so that my pictures in the end are as nice as possible, but for the general conjecture, this is not at all important. Not even that this is convex. Okay, and edges will be labeled by, so we should imagine that over each edge there's a special Lagrangian in the fiber sitting. Edges are labeled by semi-stable objects of my fiber category. And they need to fit together at the vertices. If you have a trivalent vertex, they should form a triangle, and the data of that triangle is part of the data of the spectral network. So, triangle at trivalent vertices. And then for higher vertices, you get representation AN quiver. And important condition which makes this stable object is that the total phase should, for special Lagrangian total phase should be constant. So here the argument, like in Maxim's talk, argument of omega restricted to some edge. Condition for all edges, argument of the edge, and then add phase of the object on the edge. This should be some constant, some real number which is independent of the edge.
And we're discussing the stability condition here where the phase of the object on the edge could have been interpreted as argument of form on the edge and the fiber if I had chosen the representation of that category in that way.
Yeah, that's how you can think of it, Jimmy. And yeah, there's some a little bit involved part of the definition is this other ways to do it, but there should be some. So if you have an object like that, it's not guaranteed. There's this usually in the Fukaya category definition. You have this found in co-chain technology. So if you have something like that, it's not necessarily an object of the category.
And so there are edges that run away to infinity, like in Maxim's model. Yeah.
No, it's not going to infinity. Everything is staying inside this regular n plus 1 gon, and edges are going to these vertices.
Endpoints. I didn't understand.
Endpoints are
what does
are n plus first roots of unity.
I mean, the picture doesn't seem to. So where do these edges end, which are going out?
Yeah, these are supposed to be roots of unity.
But there are also other vertices, not roots of function, right?
Endpoints of the graph, not of the edges.
Okay. So everything is going on inside the regular polygon.
Yeah. I mean, if I had something that goes outside, it does not have this balancing condition everywhere.
But you cannot have edges which connect different roots of unity with each other, right? Only they go inside.
They could go like this, yeah. Just a
It
single
could
edge
be,
like this,
okay.
yeah.
Or diagonal also.
Yeah. Inside the closed envelope.
Yeah. It's just that it has to be planar diagonal, so they don't intersect.
I mean, if there's some intersection, I can treat it as an additional vertex. Yeah, and then there's some boundary cochain. Just some solution to Moroccan equation. So I'll not worry about that very much in this talk. See the examples would become overkill. If the whole thing is a tree, then definitely there will be such a solution.
But
My-
we're drawing the picture in this metric, right? So the straight line.
Straight with respect to this flat metric. Yeah.
And so polygon for this metric is the same as ordinary one in this, if you make a change of coordinates. Yeah?
Sorry, what?
I mean, we can draw in the ordinates where the metric is just dx squared plus dy squared.
Yeah, that's this map here, right? And everything that goes out on outside doesn't really matter for us. Okay, so let's look first at the finite examples. There's 3 of them. I mean, I could also take my fiber to be A1, but then all these spectral networks will just be a single straight line. Not, nothing new really, but yeah, if I take non-trivial product, yeah, this A2 has really 3 indecomposable objects up to shift. And the central charges. So these are the 3 indecomposable representation of the A2 quiver. Into some triangle. C of A. This is going on in the fiber, C of B. Yeah, so all the spectral networks. My slide? Ah,
But you can turn it.
I think I have until 15, 10 minutes. Okay, so I'll spend 5 minutes on this example, and then 5 minutes on the next. Okay, so here, or maybe less. So here we have the basis of triangle, and spectral networks. Well, we can just connect them through these one edge of the triangle, straight line, with no vertices, and then labeled by one of these 3 objects, which are all stable.
But we started at 20, right? So there's 15 more minutes.
What are the yellow lines?
I'm just drawing this for reference, this original n+1 gamma. Now n is equal to 2. So we have that triangle. So branch cuts over here. Yeah, or of course I could put either B or C. And this condition is automatically satisfied because it's just one edge, so it's just one number. It doesn't need to be equal to anything else. But then you have the one new case where you have a single trivalent vertex. And these things are labeled some order. Either one of the 2.
So the thing happening at the infinite point, it is a vertex or it's not a vertex?
This is a vertex.
No, but the ones at the infinite points.
You don't consider 1 valent vertices. Nothing special happens. You just need to give 3 objects and then a triangle at that vertex, which is just the triangle we have in A2.
And
Yeah,
it
so-
specifies some arbitrary objects on the other three.
Semi-stable objects, and they should fit into a triangle.
No,
And,
but on the other three edges.
these are not edges of the graph. They're just vertices.
Okay.
The entire graph is just one trivial vertex. Okay.
It should be this way.
Yeah. So you can put cyclic permutation. You get some different phase. So overall, there are going to be 12 spectral networks up to overall shift. So 9 coming from these sort of diagrams where you choose one edge of the triangle and choose one object in the fiber. And then 3 coming from these sort of diagrams where you cyclically permute ABC. And remember, A2 tensor A2 is actually D4. And D4 has exactly 12 indecomposable objects. So this tells us that this corresponds to the stability condition where every indecomposable representation of this D4 guy is actually stable.
So what role is played by this omega thing? I mean, other than you have m, so you have m plus 1 bond. If you're using flat coordinates,
Yeah, in general, I could choose some different polynomial,
right.
not just a monomial, and then I would maybe get some irregular, and then I could also get things which that take the convex of these points. I get some combination of polygons and straight edges, and so all these spectral networks would be on some union of some straight edges and polygons. I'm just looking at the most symmetric case.
But combinatorics doesn't depend on this polynomial or only on the degree? Or
The set of spectral networks will completely. The category doesn't depend on the polynomial, but the stability condition and the set of spectral networks very sensitively depends on exactly what polynomial do I take. Right? 'Cause otherwise, I have some other straight lines. Because the whole thing needs to end at the vertices.
So Fabian, another question while we're discussing the straight lines. So the roots of unity here, they really come as they are the roots of unity in the flat coordinate, and they correspond to the roots of -1 in the original z coordinate. The redirections for the exponential roots to 0. Is that correct?
Yeah, up to some sign maybe.
Okay.
Yeah, it should be directions where the polynomial, real part of the polynomial
Okay,
becomes
it's minus
very
one.
nice. Yeah, maybe sign. Okay, so and similar thing works for A2 tensor A3 and A2 tensor A4, and then you get 112 spectral networks in the A2 tensor A4 case. So you construct a stability condition where all the indecomposable representations of E8 you see as some tree in a pentagon.
120, huh?
Positive roots for E8.
Not 12, 120.
120. And you can draw a picture for each of these 120 like yeah, so since I'm very short on time, this more interesting case, which is A2 tensor A5. And yeah, since it's just some curve, it's very easy to construct stability conditions, just slope stability. Gives some particular stability condition. So this has really a 10-dimensional space of stability condition. It's A2 tensor A5. Stability condition. But you get some very kind of two-dimensional, some very special ones if you consider slope stability. And these are the ones you get also from this product. Yeah, and then this, yeah, when you use the fact that everything is somehow very simple, in principle you have, for a stability condition, for each slope you have some set of stable objects. But like what happens for elliptic curve, that because there's so many autoequivalences of the categories, so this SL 2C, some central extension, this acts on the elliptic curve, and it descends to this quotient elliptic curve mod C mod 6. So it will act on this A2 tensor A5, just like for elliptic curve, and the consequence that actually for each rational slope you have the same set of stable objects. for the elliptic curve, I think of the mirror T2, it's kind of very boring because you always have just the circles, one parameter family loops. But here it turns out the graphs actually look very different depending on what exactly the slope is. So yeah, what are the stable? So for slope 0, so the new thing that happens is I don't just have trees, but I can have, so my base is now a hexagon. So I can have things like this, suitably labeled depending on by ABC. And this moves in some one parameter family, which is the size of that hexagon. And I mean, this one parameter family is, right, as we expect, since this is basically P1 with 3 overfold points, with some kind of 3 special points in the moduli space where something different happens, and you can see that if the area in the limit where the area where this hexagon coincides with the outer hexagon of my boundary, in which everything is contained. The whole thing splits into 6 spectral networks, which are these edges. So this is at the C mod 6 orbifold point of this P1. And if the size of this area of this hexagon becomes very small, then there's actually 2 ways in which it can decompose. Either like this, into 2 spectral networks, representing these C mod 2 orbifold point, or it can split just into segments into 3 straight lines, which represent the skyscraper sheaf at this C mod 3 orbifold point. There's different skyscraper sheaves you can have at an orbifold point.
It's for the small size, It's for the small size.
Yeah,
Splitting. I mean,
small area. Okay, so and that's what I said, that how if you don't know that this A2 tensor A5 is this dB of the stacky P1, if you look at spectral networks of slope 0, you see this stacky P1 as a moduli space. Yeah, and I'm sweeping some things under the rug here about bounding cochains and exactly how to fit this into the Fukaya category. How much time do I have?
This one look more like a real one parameter family than complex one parameter family.
5 minutes. Yeah.
5 minutes, okay. Yeah, I mean, you should, this, yeah, it depends on, usually the Fukaya category will be defined over a non-Archimedean field. And then this one parameter, which is this interval, will be a skeleton for this non-Archimedean P1. Or you can, like, what happens for the elliptic curve, right? The circle, there's just one parameter of the circle on the torus. And the second parameter is the monodromy. And here is, think of that, there's some monodromy as you go around this hexagon, which gives you the other parameters. Yeah, and so the same thing should be true somehow for every phase. We should find a one parameter family of spectral networks. By this huge symmetry of the category, it should be a one parameter family of spectral networks, which sloped, rational, and should be kind of the special rigid spectral networks, which appear in the limit. And this is where how do I activate?
No, you cannot.
I cannot.
Yeah.
Oh, I thought I could. But
no, you can show it to people with a good.
Aha.
Yes.
So yeah, there's kind of an Euclidean algorithm type procedure where you can start with one of these guys and
You
add
can
more
turn the
stuff.
screen around. Right?
Yeah, I'll turn. Yeah,
Turn the screen.
yeah.
Maybe
Better to show the picture than
maybe
to wave my
dim
hands.
the light so
So you start with some spectral network, which is one of these guys, and there's a canonical each time you have.
Can you stop moving it so that
Yeah, okay, yeah.
Oh, it's better.
Yeah,
like
look at
this.
that.
Yeah.
So you get just kind of bunch
So you,
of
at each, you kind of, like every rational number you can reach by, take 2 generators of this SL2C, and then you should get every rational number. And there's a canonical procedure how you can, starting from one of these spectral networks, at each step you have two choices, kind of left to right, and you eventually construct all spectral networks for all rational states. If you, I can explain to you in more detail, maybe, if you're interested. Okay, so thanks. I'll stop here.
So, any question?
And then the wild case you can use these pictures.
Well, in the wild case, you can never hope to draw all spectral networks. Because
if one factors A2 will be still kind of 3-valent graphs,
yeah, but, okay.
If the fiber catcher is
Yeah, but it was all graphs.
yeah, but
That is just, like for the elliptic curve, the mirror symmetry somehow gives a very nice picture of all the indecomposable vector bundles on the elliptic curve. And then the point of this is the same thing for this stack EP1. You can have sort of a nice picture, some actual graph for each object, stable object, indecomposable in this category. Yeah.
Haiden, I'm confused. So your stability, you have a bijection between indecomposable and stables?
no, it's in very special places.
Yeah, but in general,
In
it's
general,
the same?
of course, no.
No.
Specific stability condition.
Yeah, this I understand. I mean these pictures. It's just for
In
this
wild
very
case,
specific.
I think it's just not every indecomposable.
Yeah.
Not every.
Yeah, I understand, but I mean so this description, it's only for this special stability which is symmetric.
Oh, I have a question. You think, can you get the full 10-dimensional space of stability condition by varying the positions of the points?
I mean, you get some other set of spectral networks, and there'll be much less symmetry.
Yeah, but even just like locally, I mean, if you deform a little bit the set of points, the
Yeah.
positions of the points, is that going to give what you just at least locally the full 10 parameters?
Now, if you can cross some balls, even if you just move a little bit.
But isn't this what you guys proved in your paper with Kinsevich, Kasarkov? That you get the whole space, that you get the whole 10-dimensional space?
It's no coefficients. Yeah.
For AN.
No
determined,
coefficients. But the same proof doesn't work somehow with coefficients.
Yeah, if you have constant.
Yeah, no, it's different. You definitely need to do something very different.
I had so I observed you didn't state any theorem. So
It's a little bit work in progress.
No, but so is it a theorem that says that there exists a stability condition with these stable objects and somehow central charge given by this formula? Is that somehow?
So it's easy to construct stability condition on here, just slope stability. Central charge is equal to I times rank plus.
Yes.
And on curves, it's easy, kind of on the B side, to construct stability.
Yes.
And you can determine, you can have a list of all stable objects because of all the symmetry of the category, like for the elliptic curve.
So you're
And
saying
now
you can,
what I'm doing is that each stable object, for some stability condition which I constructed here in a different way,
but it's a theorem that the thing you constructed in a different way is a stability condition.
the theorem is just that every stable object for a particular stability condition,
Yes.
which I can construct on the B side,
Yes.
there is a spectral network.
Okay.
It's
Kind of like Donaldson Uhlenbeck-Yarrow, but
It's
version.
kind of a tame case, yeah.
It's 10 case, yeah.
Yeah, because
So-
12 case, it's
But at this moment, there's not general theorem that says these are the stable objects for some stability condition, even in this generality of A P tensor A Q.
No.
Ah.
Yeah, I mean, the point of this talk was just
Yeah,
to
no,
give illustrate a little bit
I
another
understand.
example of what
I understand.
is happening
this computer
in the
program
general.
kind of ruined your talk, yeah.
Yeah, the highlight was supposed to be this one slide.
Sorry.
Okay, can I ask a question?
Yeah.
So these spaces of stability condition, they are kind of configuration spaces of fundamental group is some kind of braid group of some Foxter group, yes? And can you see that in this picture?
In this case, it's, I don't know exactly what it has. It's very complex.
What? No,
For AN, usually have AN.
but isn't that configuration space? So this, what is this 10-dimensional manifold here, for example?
It's it's already for again you get n-dimensional manifold, which is pretty ugly. Especially this kind of like exponent of polynomial degree plus one in period making.
So it's a.
It's already ugly.
But topologically, what does it look like?
Oh, it's topology.
Globally or what?
Probably contractible.
But is there some group acting on it?
Exactly.
I mean, it's SLTC. It's
Yes,
yeah.
it's
Okay.
Okay, so I mean, let's thank Fabian again.